Okay, before I do this example, I want you to think about what it would look like if two planes intersect. So let me see if I can draw a very crude representation of two planes intersecting. So imagine this is part of a plane in space, and then you have another plane maybe coming up like so and intersecting the first plane. Like so. Maybe we should make this dotted back here. And how would they intersect? They would intersect in a line. They would intersect in a line. If they intersect at all. They could be parallel. Okay, so let's take a look at the two equations I'm giving. These are two equations of planes. The directions say find the parametric equations of the line of intersection of the two planes. Well, this reduces to solving the system. This is a system of equations. If there is it's a dependent system, so if there is a solution, we can express all the variables of that solution in terms of either x, y, or z. So let's do that. I think the obvious thing to do is just to add the two equations together to start with, because that will eliminate the z. So treat this like a system of equations that we're going to solve. Okay, you add the two equations together, we get 3x minus 3y equals 18, or x minus 3y equals 6 if you divide by 3. So I could pretty easily put this equation in terms of either x or y. Let me put it in terms of y. So I get x equals 6 plus y. Okay. So I'm letting y act like my parameter here. Now I have x in terms of y. I have y in terms of y equals itself. Now I need z in terms of y. So let me go back to the top equation. Let me go back to the top equation and plug this in for x. Right there. And that will allow me to solve for z in terms of y. Okay. So if I do that, I get 6 plus y minus 2y plus 2z is equal to 3. Okay, so that, what does that make? 6 minus y, if I combine the y minus 2y, plus 2z equals 3. Okay, let me get this stuff to the other side and say 2z is equal to y minus 3 if I subtract 6 from both sides and add y to both sides. Or z is equal to 1/2 y minus 3/2. So this ordered triple, x equals 6 plus y, and 1/2 y minus 3/2 is the solution to that, what we would call in a different class like linear algebra, that dependent system. But it's also a representation of the parametric equations of the line. We could let x equal 6 plus y. We could let y equal y and z equal 1/2 y minus 3/2. That's what we just found. It might look a little better, be a little less awkward, if we said let y equal t. It'll at least look more familiar. If we say let y equal t, then we recover our parametric equations as x equals 6 plus t, y equals t, and z equals 1/2 t minus 3 halves. That's it. Again, the reason this works is you give me a t value, and by plugging in t into all three equations, I get an x, y, and z that's on both planes. Has to be. That's because I solved that system of equations, and the solution satisfies both equations. Therefore, these must represent the parametric equations of the line of intersection.